So I will do videos for example sets number 1 and number 2, and if you do these, the problem set number 5 is going to be pretty easy for you. So we're going to work through all of these problems here. So for the first one, if I give you p equals 0.67, q is going to be, remember this, p plus q equals 1. So if I know that, all right, I'm going to take 1 minus 0.67, and I'm going to get 0.33. And that is my Q. Right? And so what will be the Hardy-Weinberg equilibrium for this problem? So I'm going to take, we're going to have P squared. I hate it when it does this. Okay, that's going to be equal to 0.67 squared. All right, we're going to do that. We're going to be a little bit slow about this, apparently. And that's equal to 0.449. Okay, so if I just square 0.67, I get 0.449. My 2pq is going to equal 2 times 0.67 times 0.33, which equals 0.4422. And then my q squared will be 0.33 squared. I'll fix that here in a minute. And that will be 0.1089. Okay, so that term is squared. And so that's what I'm looking for on part B. So here we have some number 2. A cattle population has an occasional incidence of neurologic hydrocephalus, disease marked by the feature of newborn calves with fluid filling their head. It's a lethal recessive genetic defect. You've got a herd of 10,000 head that's been DNA tested. 5,500 of the animals were free of the defect. 4,500 were carriers. What is the genotypic frequency for the population? And so here, I'm going to denote big N as, so the capital N is the normal allele. That's going to be 5,500 over 10,000, which is equal to 0.55. Again, little n equals 4,500 over 10,000 equals 0.45. What are the gene frequencies? So for capital N, that's going to be equal to 2 times 5,500 plus 4,500. Okay, that's my numerator. And then I'm going to do brackets here. Okay. And I'm going to take that and divide that by 2 times 10,000. So order of operations here is important. So this is going to equal 15,500 over 20,000. That's what you should get. And that will be 0.775. Okay? So it's not something where you just put all this in the calculator. I would figure out this number first, which would be 15,500, and then divide that by 2 times 10,000, which is 20,000. So for my little n, I'm just going to do the same thing. It'll not do that automatic capitalization. So that's 4,500 plus 2 times 0. Okay, because I don't have any individuals in the herd that have 2 copies of this because they're dead. Trying to be blunt here, I guess. Okay, and divide that by 2 times 10,000 equals, you should get 0.225 on that one. All right, so 4,500 divided by 20,000. All right, so if the population were in Hardy-Weinberg equilibrium, what would be the genotypic frequencies? All right, so we're going to take these gene frequencies and then utilize those. And for capital N, that's just 0.775 squared. I'll fix that here in a minute. That's going to be 0.6006. So we're going to square this term here. For my heterozygote, it's 2pq. That's going to be 2 times 0.775 times 0.225, and that will be 0.349. And then little n will be, we're going to square the 0.225 equals 0.0506 to square that term. And so those are your Hardy-Weinberg equilibrium frequencies. Okay. So how does this compare from C to A? Well, the main thing is this one, where we have a presence of the lethal genetic defect presenting itself. So for problem number 3, you've got a Hardy-Weinberg of p squared equals 0.642 pq of 0.32 and q squared is 0.04. What you can do is just choose one of the homozygotes. So I can take p squared equals 0.64 since this is in Hardy-Weinberg. All right. And I'm just going to take the square root of 0.64 to find p. So, and that's pretty much all you do. So if I do the square root of 0.64, I'm going to get p equal to 0.8. And so likewise, if I've got 1 plus, or p plus q equals 1, if I do 1 minus 0.8, all right, so if I do 1 minus 0.8, that's going to be 0.2, and that's my q, okay? So my gene frequencies then would be 0.8 and 0.2, okay? For number 4, in a population, the incidence of dwarfism is about 4 cases out of 10,000. And so I give you 4 cases out of 10,000. That's my q squared. Okay? All right? So q squared is 4 out of 10,000. So that is, find the genotypic frequency q squared of the gene. So that is the answer, 4 out of 10,000. So when I find the gene frequencies, first I'm going to find q, all right? And how I find q? I'm just going to take the square root of q squared, which is the square root of 4 over 10,000, all right? Do the square root of that, and you should get 0.02, all right? So then if I want to find p, that's just 1 minus q. So that's just 1 minus 0.02. And so my p then is 0.98. All right. So to find the q here, all I'm going to do is square root this number up here, and I will get 0.02. All right. Problem C. Find the genotypic frequencies if the population is Hardy-Weinberg equilibrium. So then I'm just going to find p squared, 2pq, and q squared. PQ and q squared here. Right. We'll get there. So for this, I'm just going to say 0.98, square that, put that in a little different notation there, and I get 0.9604. For 2pq, this is 2 times 0.98 times 0.02, and that equals 0.0392. And for my q squared, this is just 0.02. Okay. Let me redo that because I don't think that's right. Because that was my gene frequency. Okay. If you do 0.02 times 0.02, yeah, I can put it in my calculator right. That's 0.0004. I thought something was up with that. And so all of this will add up to 1, and that's what the answer will be. Okay. Number 5, another type of dwarfism is dominant in certain individuals, and there are 2.5 cases out of 10,000. Right? And so this example here, I won't work through it. You basically are doing the same thing that you did up here on number 4. So I'll give you the answers, but you can work through it. So on this first one, it should be 2.5 over 10,000. All right, my gene frequencies, Q is going to be equal to 0.016. And my P will be equal to 0.984. And for my genotypic frequencies, P squared is 0.968. So you should get 0.968 for P squared. 0.0315 for QPQ. And Q squared. Hang on, let me add it. Make sure it's all on the same page. Is going to be equal to 0.00025. Right? So that's what you should get. And we're doing the same process that we did in the previous problem. Okay. Number 6. All right. This is basically the same as problem number 1, just with a little bit different numbers. So if P equals 0.35, Q is going to be equal to 0.65. Because 1 minus 0.35 is 0.65. My P squared will be 0.1225. QPQ is 0.455. And Q squared is 0.4225. All right. So figure out, basically look at problem number 1, how we did it there. All right. And you're going to do the same thing on problem number 6. Okay. Number 7. What will be the allelic frequency of an allele that is lost in a population? So we're talking about something of where no animals have that allele in the population. So if that is the case, that allele frequency is 0. All right. Now, if you have a situation like a number 8 of where all animals have only that allele, all right, so it's 100% of the animals have 2 copies of that allele, so it's fixed. That's a situation of where the gene frequency is 1.